Okay, so I'm walking home after a long, terrible day at work. The printer jammed, I got a paper cut, somebody stole my tuna casserole lunch from the fridge. It was awful. And then out of nowhere, it starts pouring rain, and I forgot my umbrella. To console myself, I dip into my favorite chain coffee shop, Tom Jordan's. Now I'd hit rock bottom at this point, but seeing Aurora, my favorite barista, improved my mood, and better yet, I realized it was Roll the Wheel month, which only happens once a year and gives each customer a shot at a free coffee, or better yet, a free muffin. Aurora rolls the wheel for me, and bam! I get a free muffin! What are the chances? What are the chances? I'm Sabrina Cruz, gourmet muffin fiend, and this is Study Hall, real-world statistics. Probability is a lot more than just cute coincidences that can fix your horrible, no good, very bad day. It's the tide of uncertainty we have to surf to make it through life. But if you know the rules, it's a piece of muffin. Probabilities are how we think about chance in terms of numbers, because a hunch doesn't cut it when muffins are at stake. With probabilities, we are describing the certainty or the chances of some event happening as a number between 0, or no chance, and 1, a 100% guarantee. Basically, probabilities give us handy tools for making the best possible guesses or decisions despite uncertainty. What's more, they are essential for letting us know how certain we can be about the estimates and guesses we make using data. For instance, every Roll the Wheel month, customers at my favorite Tom Jordan spot have a shot at glory. The two baristas, Aurora and Carlos, have a little wheel set up behind the counter they spin. And if the little arrow on the top winds up in a section corresponding to the prizes, the customer gets a free muffin or a free coffee. Or if it lands in the loser zone, they get nothing. It's a little harsh, wheel. The thrill of possibly landing a treat keeps customers coming back. That's good news for Tom Jordan's, which wants more customers. But it's also good for people like me, who really enjoy free food, especially when we've had a bad day. During Roll the Wheel month, Tom Jordan's makes your odds of victory pretty good. The wheel is split up so that the first wedge in the circle, occupying 30%, represents winning a muffin, while the next wedge, occupying 50%, represents a free coffee, with the remaining 20% falling into the loser zone. If you're like me and your goal in life is to never lose at anything ever, things like the wheel require some planning if you want the best odds of winning a muffin. But it also requires planning for the staff at Tom Jordan's. For instance, the probability of the wheel landing on the muffin helps them calculate how many muffins to bake for return customers. Now, if your goal is to win a muffin, your mind might already be jumping to saying I've got a 30% chance, because that's the proportional area for muffin on the wheel. But whether or not that's true comes down to one crucial thing: dependence. Dependence is when a probability depends on another outcome. For our purposes, the wheel always starts at the same place, no matter what. And when Aurora spins the wheel, she gives it a good old shove, and the wheel truly has a random chance of winding up anywhere. In that case, the probability really is 30%. But her colleague Carlos is a bit more timid and just gives the wheel a little tap. The wheel barely makes it halfway most of the time Carlos is on shift, and lucky customers now have a 50% chance of landing a free muffin. Basically, in our hyper-specific cafe scenario, the true probability of nabbing a free muffin depends on which barista's on shift. In math notation, the probability of a muffin, given that Carlos is on shift, is written with a straight line, like so. Probabilities that are describing some kind of potential dependence with this given that symbol inside them are called conditional probabilities, because they refer to a certain condition surrounding the event we're interested in, like who's on shift. Now, Tom Jordan's is not in the charity business. To reinforce the original odds, Carlos's manager informs him that he's gonna need to step it up with his wheel spinning. Now he spins the wheel just as hard as Aurora does, and the situation changes. Regardless of who's on shift, customers have a 30% chance of a free muffin. In other words, the probability is now independent of the barista. In math lingo, we write this by saying the overall probability of the outcome is equal to the probability given some other condition. In fact, this condition defines when a probability can be called independent. But remember, if the overall probability isn't equal to a conditional probability, it's still called dependent. Dependence and independence are really important concepts for understanding when two things might be related and also when they aren't. Like, the probability of me losing my appetite for dinner depends on whatever muffin I just ate. But my appetite probably doesn't depend very much on, say, the color of my socks. which is white, in case you're wondering. I'm a very boring person. All of this is crucial when we want to calculate the probability of two events. For instance, say one of the other Tom Jordan's regulars, Mir, comes in twice in one day and both times has a spin at the wheel. What are the chances he wins a coffee during his first visit and a muffin during his second? When we want to talk about the probability of multiple outcomes happening, we'd write them with this upside-down U-shaped symbol, which means intersection, like where the two outcomes intersect. This is basically another way of saying and. As for how we actually calculate this overall probability, the spin of the wheel doesn't depend on earlier outcomes, so the probabilities are independent. In this case, we can simply multiply the two probabilities for the overall probability, which gives us 15%. This holds for any case with independent probabilities. Maybe we want the probability for the intersection of lots of independent probabilities, basically the chance all of these unrelated outcomes come to pass. In that case, we can simply multiply all of their individual probabilities. But when the probabilities are dependent, the math shakes out differently. For instance, before his manager gave Carlos a heads up about the wheel, what would Mir's chances have been at nabbing a free muffin from him? Specifically, what's the probability that Carlos was on shift and that Mir got a free muffin? To answer this, we need one more piece of information: the probability of Carlos being on shift. It turns out Aurora and Carlos split the shifts at the cafe 50-50 at pretty much random, so it's 50%. Yes, they are very understaffed at this Tom Jordan's. Now, we can't just multiply the odds of Carlos being on shift and the odds of winning a muffin, because, as we saw previously, the probability of a muffin depends on who's on shift. So we just need one little tweak to account for this. If there's a dependence between the events we're trying to find the intersection for, all we need to do is replace the independent probabilities with the dependent one. In other words, the chance that Carlos is on shift and that Mir gets a free muffin is the probability Carlos is on shift multiplied by the conditional probability of a muffin given that he's on shift. This general pattern holds true when calculating probabilities about the intersection of dependent events, and with a little rearrangement, we can actually use this same formula to learn about conditional probabilities. For instance, before Carlos got a talking to, maybe Mir suspected he had better odds of winning some sweet muffiny goodness when Carlos was on shift, but didn't know what that probability was. In other words, what if Mir wanted to work out the conditional probability of winning a muffin when Carlos is on shift? Well, by using the probability of Carlos being on shift and him winning a muffin, which he could work out by counting the number of times it happened, and knowing Carlos was on shift 50% of the time, a rearrangement of our formula from earlier could help him calculate exactly that. And that's also how we can more generally define and calculate conditional probabilities. But sometimes the answer is also just plain obvious. Like, we can immediately say that the probability of a customer winning a coffee and a muffin is 0. The dial can only land on one section. When the intersection of two events is 0, meaning that two things cannot happen at the exact same time, we say that they're mutually exclusive. If one happens, the other definitely can't happen. Then there's this sort of wide U, which stands for union. That might make it sound like both of these things are happening, but when you see it, what it really means is that at least one event has to happen. And that probability isn't 0 because it's definitely possible for a customer to win one or the other. When we're dealing with the probability of the union of two events that are mutually exclusive, all we have to do is add up the two probabilities together. But say bakers at Tom Jordan's accidentally make too many muffins one day and they need to get rid of them fast, and they don't just want to give it to me. The staff might temporarily draw on a slice of the wheel corresponding to coffee, splitting it into a both just coffee part and a coffee and muffin prize, which takes up 10% of the wheel. In situations like this, we'd have to account for how the probability of winning a coffee and a muffin is no longer mutually exclusive, which means we have to calculate the probability of their union differently. And the probability of winning a muffin under any circumstance has now shot up to 40%. The way we tackle this is simply by tweaking our rule for adding up probabilities, by subtracting the probability of the intersection of the two events. That way we have the probability of getting a muffin or a coffee, but not both. If that's confusing, it can help to see it laid out, which we can do with a contingency table. Contingency tables lay out all our different outcomes and the probabilities associated with them. We place all the possible outcomes on one variable, like winning a coffee or not, along a row, and the possibilities of another event, like winning a muffin, along the columns. This maps out all the possible combinations, which should add up to 100%. For instance, if we throw in all the probabilities we were just working with for winning a coffee, muffin, or both, the contingency table has one blank spot, the probability of not winning a coffee or a muffin. Since all the possibilities need to add up to 100%, all we need to do is subtract all of the other numbers from 100 and hey presto, we have our odds of not winning any prize. The same logic works for getting the probability in any other cell of the table too, provided we have the other values. Another neat way of visualizing all possible outcomes is a Venn diagram. Each outcome is represented by a circle, with the overlap representing both events happening and the parts outside each circle representing the probability that that event doesn't happen. For instance, if we plot our contingency diagram as a Venn diagram, it would look a little like this. The cool thing about Venn diagrams is we can also add in a third variable like this, or even a fourth, although from there, things can get a little messy. In general, we want to keep things visually neat since that's when both contingency tables and Venn diagrams shine. And while those overlapping circles might seem pretty basic, they have important real-world uses. For example, in bioinformatics, scientists use Venn diagrams to display how certain genes are linked with the risk of different diseases and health outcomes based on how they overlap between circles representing those outcomes. In those cases, the diagrams become an easy way to show a problem visually to a wide audience. Whether you're a doctor out there saving lives, an unlucky person trying to win free muffins, or a goat enthusiast participating in a game show, understanding conditional probabilities is at the heart of statistical analysis. But it's also super important as you go about your daily life. We frequently use data to investigate how two or more things are related. Did the new coffee shop down the street increase the neighborhood's house prices? How might we anticipate a patient's risk of developing cancer or diabetes? What are our odds of winning a goat versus a car when we open a door? These are all questions that rely on reasoning about relationships, and understanding how to work through these dynamics gives you the tools to cut through the noise all around us and think clearly about uncertain situations. If you're enjoying this series and are interested in taking the full study hall real-world statistics course and earning college credit from ASU, check out gostudyhall.com or click on the button to learn more. And if you want to help us out, give this video a like, smash that subscribe button, and comment your favorite type of muffin. If it isn't chocolate, you're wrong. Thanks for watching, and see you next time.